Okay. Here we go. So now you guys have all the. I need to clean these up as well. Pass those around. Pass those around.
Oh.
We'll at least partially cover curve sketching today, so here's the handout for curve sketching.
No, we can roll over exam too. I go with us.
So there's that. And I have some more stuff here.
No, that's
Okay, so I already put some comments on the test in the email. And also, if you guys want to talk to me today after class, I'll view that. So we can talk about your test and the mistakes that you personally made. That's ones. But the general comments were, and again, I told you, I sent a rant to you guys about this in email. Know the rules was the first one. Right, so in problem 4, part 1, all I asked you guys was to just write the rules down. Didn't have to do anything, didn't have to figure anything out, didn't have to calculate anything. Just write down the rules. Pretty much everyone got that wrong. There were like 2 people, one person got it all right, and then another person got like one of them wrong. And pretty much everyone else messed up almost everything else. So yeah, knowing the rules, that is so important, so important. Like, I cannot emphasize to you how important this is. If you don't know the rules, you haven't studied. I don't care how many hours you think you put in. If you can't say the rule, you haven't started studying. You haven't even started, right? I spent 4 hours on homework. Okay, write down the power rule. You can't do that, you haven't studied. Know the rules. They tell you everything. Some people go overboard with the rules. I didn't mention that in class, but there was this problem. Remember that guy? Pretty much everyone did the quotient rule here. Why would you do the quotient? Just simplify. That's 5 over 2x squared plus 3 over 2x. It's a power rule problem, right? Remember, the first thing you're going to want to look for is to try and simplify things, right? So, yeah, pretty much everyone tried to do the quotient rule there, and most people did the quotient rule incorrectly.
Here's another thing, like that problem. It's like,
Yeah.
how does one know what to do what? Like in this case, it's 5 halves x squared plus 3 halves x. So
Yeah.
how does one know when to just factor out an x, or how does one know when one can bring up the denominators in negative power, or when they can't, or like that's all those weird. That's what
Right, there's a strategy. You literally always try to simplify first. Always. It's always the first thing you look for. All the time. So if you saw something like this, which was the part C, right? Even that, the first time I look at that, I would think, can I simplify this? I don't want to use a quotient rule. Turns out I couldn't. There was nothing I could really do here. You could do a long division, but it really wouldn't help you. I mean, technically, you could have written this as something like 1 minus 5 over 5 plus x to the 5th, but you still have that guy, and it will get to too much trouble to go here. So, but yeah, like simplifying is always something you think of doing. You always look at that, right? Especially if you see like fractions, the quotient rule is kind of an annoying thing to do. You don't do it unless you have to do it, right? Once you have a single term in your denominator, you try to divide it in. If you have a constant on top or on bottom, you try to separate it, right? This was something I mentioned when we went over the quotient rule. You always try to not use it, right? You kind of use it when you have to. And if you were going to use it though, if you did the quotient rule and you actually got it right, then I would have given you the credit, but it was overkill. Like this person did, they actually got it right. But I wrote, it's overkill, like you're working too hard, right? A lot of these things you want to be able to simplify and recognize what these functions are. Yeah, for some reason, a lot of people, I have in a problem 2 to the x, a lot of people thought that was 2x. It seems clear to me that that's the power here. Or maybe they just pretended. They didn't know how to deal with this, so they're like, let me pretend that I can't read it. I don't know. Yeah, so that was 2 to the power x. By the way, what's the derivative of that?
It's 1 times 2 to the power of x times ln of 2.
Yep.
Wait, which one was that?
He knows. That was in part D. It was under a radical. But that would be the derivative of the inside function. What else? Yeah. So in problem 1, yeah, I didn't scan the solutions. I'll have to scan them and post them to you. In problem 1, a lot of people had trouble simplifying the fractions. That's another thing. In part B, though, that was the main concern. There are some people who did problem 1 incorrectly, which, by the way, you could have actually, right, that was your function, right? Remember I said, at this point, we actually know all the shortcuts. We know the rules, right? So you kind of know what answer you should be getting, right? So if that's your function, what's the derivative?
2 plus 3 over x squared.
Right. So you know the answer. You know that's what you should get. If you get something else, it should kind of jump out at you, right? I mean, this is a simple power rule problem. So you know what answer you should be getting, right? So I saw a lot of crazy answers there. If you got a crazy answer for part A, but you used that correctly in part B, I would have given you full credit for part B. Some things that I didn't get in part B were, some people were giving me equations where they're actually, like they would literally plug this into the equation of a line. So they'd write something like, the coordinate I think was, it was like 1 comma minus 1, right? So the point was 1 comma minus 1, right? Because you plug in, to find the y value, you plug in the x value into the first one. Right, so that was the point. And I saw people do something like this. Y minus y1 equals m. And for m, they literally wrote this down. Times x minus x1. So what's the problem with that?
It's not a slope.
It's not a line. Lines look like, right? As in on the right side, the only variable is an x and its power is a 1. There is a square here. It's not a line if it doesn't look like this, right? Like to write this down, it's like, you should know what the equation of a line looks like. You should have known that since algebra class, right? If you have squares, it's not a line. Like, how could you write that down as an answer, right? What you had to do is you had to plug 1 into the derivative, get a constant, and then you put that here. It has to be a constant. Your m is a constant. It's not a line if this is not a constant. It's a constant times x plus a constant. That's a line. Right? So if you write anything else, your x has any power, there's a radical, there's an exponential, there's any other function other than x to the first power, it's not a line anymore, right? If you have an x in a denominator, it's not a line anymore. It has to look like this to be a line. If it doesn't look like this, it's not a line, right? So that was something that jumped out at me in problem 1. Problem 2 was, it's kind of half and half. Like a lot of people kind of knew what they were doing, but mostly algebraic mistakes. A lot of people forgot that pi squared was actually a constant. Derivative is 0. A lot of people differentiate that and said it's 2 pi. It's not, right? Because they don't know the rules. What does the rule say? X to the n is nx to the n minus 1. The base has to be an x. Here the base is not an x. This rule does not apply, right? If you knew this rule, like really knew the rule, you would have never made that mistake. It doesn't match. This pi is not a variable. It's not an x, right? The derivative is 0. It's a constant. Yeah, like I said, part A, I would have simplified. I wouldn't have used the quotient rule there. And literally, every time I see a division, I'm going to try to look if it can be simplified. Can I factor and cancel something so I don't have to use the quotient rule?
But again, referring back to the y equals x to the power of 5th over 5 plus x to the 5th, like, how does one know that as to whether or not we can take 5 plus x to the 5th in the denominator and just put that in parentheses as that to the power of -1?
You could do that. That is also an option, right? Like if you really hate the quotient rule, you could have written this as this and use the product rule. And when you're differentiating this part, you need the chain rule. That is an option. That I don't particularly think is worth it. But if you have a personal preference, there's nothing wrong with doing that. Here, I would just have used the quotient rule, but if you really like the product rule, you can do that. The only time when I think of manipulating it like that is if the top or the bottom is a constant. Otherwise, I just try to divide. And not many people made this mistake, but notice that I think I saw it once. Like, you cannot split a fraction across the denominator, right? So this is not the same as saying that. Right? That's not the same thing. I maybe saw one person do that. Not many people do that. But you should know, like, you can't split up the denominator in a fraction. Right? You can split the numerator. You can't split the denominator. Yeah, the implicit differentiation one, I think actually most people were on the right track there. Yeah, so for the velocity one, part A, almost everyone got. The other parts though, I think some people got confused. And that was one of the things I spoke about in the email, right? About reading the problem carefully and giving what's asked for. So like in part D, I asked for what is the velocity when Javon hits the ground, and a lot of people gave me time. Like I didn't ask you for time, I asked you for velocity. Why are you telling me the time? Part C asked you for the time. Yeah, so problem 4 was about the, problem 4 part 2, that was using the linear approximation formula, which I think it's about half and half. Like half of you guys totally forgot the formula.
Well, to me, it was just like, okay, so
we're talking about 4 part 2.
Yeah, we're talking about
we're
talking about number 4 part 2. Well, isn't f prime of a, well, f of a is a constant, like it's the cube root of
yes.
radical.
You have to know what a is. So in 4 part 2, you would have chosen f of x to be just the cube root of x. And so your f prime would be 1 over 3 times the cube root of x squared.
But then when you get to,
yeah, so then you have to know who's your x and who's your a, right? Your x was 27.1, your a is just 27.
But then if prime of A, it's like you plug A into
27 to here. Yeah.
No.
Yeah. So here you have your f of a will now give you 27. You put in here, you get 3, and here you have your f prime of a. You have 1 over 3 times the cube root of 27 squared. Cube root of 27 is 3. 3 squared is 9. 9 times 3 is 27, so that's just 1 over 27. And you plug that into the formula. So about half of you got that one wrong, but I think it's just you guys didn't memorize the formula. Or at least you didn't memorize what the pieces in the formula meant. What was the x, what was the a, what you should be plugging into at a certain time. Yeah, problem 5. Some people skip like this problem completely. So I gave you the cost function. What is the revenue function?
Number of items sold times profit. Wait, did you say marginal revenue?
Yeah, so in part A, so 5, I gave you the cost function for something, and in part A, I actually defined the revenue function and the profit function. Right. So what's revenue? It's x times.
5.
No.
C.
X times P, right? As in the price. Revenue is just how much money I make by selling. So it's the number of things I sell times the cost, the price that I sell them, right? So R is just 5x in this case, right? Because I'm selling for $5 each, right? Your profit function would just be the revenue function minus your costs, right? Profit is how much money you make when you subtract your costs. So it's just going to be 5x minus the function I gave you. And of course, the marginal, you just differentiate the two. The C prime would be the marginal cost, and R prime will be the marginal revenue. The answer to C, that's just remembering that the derivative works as predicting the one more element. So if I know I made 6, C prime of 6 is an approximation for how much it will cost to make the 7. Some people were close there, they used C prime of 7. No, you had to use C prime of 6.
Because you use prime 6 and then it's like the other one that you used.
No, that was it. That was the only way to do it. I specifically said in the instructions, use the marginal cost to approximate. That's how you'd approximate. C prime of x gives you...
What's marginal revenue again?
The derivative of revenue. Marginal just means take derivative, right? But it's just an approximation of what the result is of making one more unit, right? So C prime of x is roughly the cost that it would take to make x plus 1 units.
You got RX from X is just X and P is just 5.
Yeah, P was 5, which I told you. I'm selling for $5. So that's that. And so here I'd actually write down the formula. This is 5x minus, and I put the cost function here. And as for whether it's good for business, you notice that this function here is actually an upside down parabola, right? Because there was a plus 2x squared here, right? And it's now minus, right? So what does that mean?
I put no, but I ain't got a comment right there. So
The more hot dogs I sell, what's going to happen?
that's more money.
I'm making less money. How is that good for business? Right? If I sell more, I should make more. Right? So no, this situation is not good for business. I would hit my peak profit very quickly. Right? I think the. By the way, break even is where the amount of money I make is equal to my cost. Break even means profit is 0, by the way. So break even means R of x is equal to C of x if you sell for x. You would have gotten 10 at that point. So once I sell 10, I break even. And my maximum profit actually occurred before that. We didn't compute that, but the thing is, I would hit my max profit pretty early, but the more I sell, the less I start to make after a while, right? And even in part C, when you did the marginal cost, it was already growing very fast, right? Like I think it cost me $4 to make the 7th hot dog, and I'm only selling for $5, that was a bad business decision. Yeah, so know the rules. For those of your economics majors, this whole thing about marginal analysis, you guys will do it again. It's not really going to be emphasized for the rest of this class. But for those of you in economics, you should start to focus on that. But yeah, know the rules. I think, what was the other things I wrote about? Oh, I wrote something about attitudes and time management or something like that. And yeah, I wrote it was a really long email. But yeah, I know a lot of you are working a lot of hours. You've got to reorganize your schedule. And you really have to sort of focus on the important things. Like, for example, knowing the rules and definitions, right? Like, if you don't have a lot of time to study, right, you have to know the most important things to study. Like, the rules are the important things to study. Even if you have to, like, skip a homework or only do half of a homework to memorize the rules, it's actually a worthy investment. Some things are more important than other things, especially when you're short on time. So as far as knowing the rules are concerned, when I say know the rules, I mean you should be able to know them, be able to regurgitate them without thinking about it, and also, I think I also mentioned this in the email, also know what the pieces are. Okay, so for example, in the power rule, which would have saved you guys a lot of trouble, right? Knowing that the base is a variable and the power is a constant means I would have not have made a mistake with that pi to the squared thing, right? Right, so I would not make the mistake of thinking the derivative of this is 2 pi, right? Because I know this rule, I can write it down without thinking about it, but I also know everything that I write down, I know exactly what it is, right? The base here is a variable, it is not a constant, right? The power is a constant, right? If this is not a constant, or that is not a variable, this rule does not apply. It's that simple. Yes?
But I literally wrote down like a times u to the a minus 1. And here it's like n times x to the n minus 1. So what?
Again, that's a different rule.
Well, that's the, yeah, I get that part.
Right, but what is the base here?
Constant.
The base is a constant. Here the base is a variable. They're two completely different things, right? Here the power is a function, right? This power is an f of x. It's some function.
But for me, I didn't write a to the power of u. I wrote u to the power of a. In which case,
you're kind of in this situation. You just rename the guys.
Yeah.
Yeah, which wasn't right. Because I specifically asked for the rule to differentiate an exponential function. That's the rule I was referring to. Right? So yeah, knowing that this is a variable and that's a constant, and the opposite, when the base is a variable and the power is a constant, these are two different things. And if both are variables, like an x to the x, neither of these would apply. Which that was in problem 2, one of them. I think I put something like this. A log differentiation. Right? Remember when we did log differentiation, I told you there are two situations in which we want to use this. If the power is a variable, or if doing the quotient rule is super annoying. Right? So here's a case where your power was a variable, meaning this rule did not apply. Because for this rule to work, that has to be an n. It has to be a constant. That is not a constant. That rule does not apply anymore. This rule does not apply anymore either, because the base is a constant. Here, the base is not a constant, the base is an x. So then you're like, what do I do now? Well, get rid of the power that you do that with a log, right? So you just ln both sides. Now you differentiate implicitly.
But that part is like, That's at the end of the problem, don't you gotta L in the whole thing or that whole side? Like, is that?
Right, there were two parts. There was this plus that, right?
Yeah.
So remember what we did in class. Separate it. Do this separately. So you go to one corner and you do this. And then you come back and you plug it in.
But Professor, in your a to the u equals blah blah blah, that u is another function.
Yes.
So why wouldn't why? Who's to say that x squared is not a function?
X squared is a function.
So then why does that rule not apply?
Because the base is a constant.
Oh.
The base is not a constant.
So when you solve for that, like you see you did it in science, then what do? You put x squared on x back into, like at the end when like you're just gonna write that.
Yeah, so like my whole function was like x squared plus that.
Yeah.
Then here I'm going to differentiate this. This would give me y prime over y is equal to, I do the product rule, I would get 2x ln x plus x, right? And so, call this something else, call this like a g or something, so I don't mix it up with my y. And so I would get my g prime is the original function, x to the x squared times 2x ln x plus x. And then I go up here and I said y prime equals, well this I know how to differentiate, that's just 2x plus, write that answer here.
Why you tell us to study the questions on the finals? I feel like the questions on the finals are easier than the test. But I'm not, that's why we failing. The question on the finals, they're easier than the test questions.
I don't know.
It's like you didn't see. I don't think you didn't say like. I feel like when we did that problem, like you would get that, and then is that all lead part where you're like, wait, is this too much?
That's a
And then you're
curveball.
What's a curveball?
That x is x squared.
Like, when you study, it's like, oh, I got this, and you get it, then you get your test done, and you got 0. Like, it makes no sense.
No. We did problems like that in class.
Are you gonna give any more quizzes? Like
Yes.
so you can get more
Monday's a
classes?
quiz. But they're good, they keep you studying. So here's what we're going to do now. We have more homework. This is from now on it's required every class. What you're going to do is go into your homework grade. Normally a homework is 2 points. I will make each sheet here, each page here is worth 4 points. I gave you a list of the rules. I have circled the ones that are important for this class. Every day you're going to write down all the rules and you're going to write down what the pieces in the rules are. So for example, in every class you're going to hand in 2 sheets. Whether or not we have homework otherwise, I don't care, you're going to hand this in. You're going to have your name. I would like you to put the date, so today is what, the 7th? Morning. You're going to put your name on the second page. Put the date. You're going to put evening. Twice a day, you will write down all the rules on this page and the meetings. So for example, you're going to list one of these rules would be the power rule. You're going to write down the rule, and then you're going to say x is a variable, n is a constant. 2, you're going to write down you're going to go through these rules, all of them. A to the u is u prime, a to the u, ln a. Then you're going to write down a is a constant, u is a function of x.
And
You're going to do this here as well. For all the rules that you see here. Including the ones, there are some that they didn't write it the way we wrote in class, so I rewrote those. So there's the chain rule I wrote up here. There's the power rule I wrote here. And for now you can probably skip the integration because we haven't covered that yet. But starting with the top part, the derivatives, like you have this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this replaces that one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, around 11 rules. So you should have a list of 11 things. You're going to write down the rule. You're going to write down what the pieces are. Every class you give this to me. 2 sheets. Date, morning and evening.
so we rewrite
You
twice a day.
rewrite twice a day all the rules. and
All the
what
rules
pieces
that are
are.
circled, like 1, 2, 3, 4, 5, 6, 9.
Yes, and all the rules that I wrote in by hand.
Oh, also, not the integration, but like the chain rule and the, yeah.
And if the rule has a name, you should probably write that down as well. So power rule.
Oh,
This rule doesn't really have a name. So when I asked it on the test, I literally took a whole sentence to describe what I meant. Yes,
So we have to do this
every class, yes. In addition to your normal homework.
Does it start today?
It starts today. So on Monday, you're going to give me 2 of them. You're going to give me 4. You give me 1 for the 7th, and then whatever date Monday is, you do that.
How did the class do?
Most people did worse than the first test.
Yeah.
I think there were like 2 people who did better. But yeah.
I appreciate the strategy for
Memorizing the rules.
Yeah. You guys won't do it on your own. I'm going to have to force you to do it at some point.
I'm just scared.
Yeah, I did flashcards, but
I do have
like everybody
flashcards
has
too.
rules written down.
I did flashcards as well. But.
What happened?
When you actually see it, it's like, what the hell rule is this? Sometimes, like that x to the x squared, it was kind of confusing.
But I also feel like the homework that we do, you know how it's like 1 through, I don't know, 51? I feel like the ones towards the end, we don't use those in the exam. So can you like make it 1 through 21? Because those are the problems that are usually more difficult. Yeah, they get more difficult
maximum
towards the
and minimum
end.
values after like question 20.
No, well, yeah, well, the homeworks,
So none.
no, the homeworks, it's pretty important for you to go through everything. Like the first time you're doing something, you really do want to look at it from many different kinds of angles, whether I'm specifically testing you on that or not. But when of course, when you're studying, you just know, ignore that part of the homework. Right, so when you're going back a second time and studying, you can just throw away all the things that aren't relevant anymore. But the first time you're seeing it, it's actually important for you to wrap your mind around the concept. You want to do things that are maybe even slightly different from what you're required to do. It also gets you used to seeing something like this on a test, right? So if you went to do the homework and you're like, this doesn't look anything like any of the finals, so you skip it, what you're doing is you're teaching your brain to, if something kind of looks weird, just avoid it, right? So then you go on a test, And your brain looks at that and is like, I'm just avoiding this, forget that. And your brain goes in flight or flight mode and you spaz out, right? You really want to not be surprised by curveballs. You want to get used to the fact of practicing things from different angles, right? So that if anything looks kind of suspicious, you're comfortable dealing with it anyway. You just break it down. You're just like, okay, freak out for a little bit, and then you're like, okay, let's think about this, right? What rule would apply here? The power rule? No, because that's not a constant. What about the a to the u rule? No, that's not a constant. And then you start to brainstorm, and eventually you come up to the idea. It's going to help you roll with the punches. So it's actually important for you to do all that stuff. Of course, you do it once, and you never really practice it again.
I don't see where that rule is on this list.
Where what rule?
The one you X to the
For x to the x squared, it's not a rule, it's a technique. Log differentiation.
I would have never known that.
What? Log differentiation.
It's in the textbook.
Okay.
Yes, it's in the textbook, and I did it in class. And I told you two situations in which you would use it. Right? Power is a variable. Right? Even if you're doing this rule, it would work in this case as well. Right? In fact, this rule was derived using log differentiation. So in the log differentiation chapter, they actually derived this rule with log differentiation. Right? So the power is a variable. Right? Or quotient rule is super annoying. Right? And I did a couple examples of this. So if on the test I threw something at you like x to the 3 halves, the radical of x cubed plus 4 times 7 to the x over 2x plus 1 cubed times the cube root of x squared plus 1. So you see something like that and you're going to think like,
I'm scared.
log differentiation is what we do, right? Because once you throw an ln on this, you can break all these guys apart. All their powers you can bring down as multiples and just apply the ln rule, right?
That's only if it's being multiplied, right?
Yeah. So in that situation, or in a situation where you have a variable as a power, it doesn't matter if the base is a constant or not. Or x squared plus 3 to the x squared. Like any of these guys, you use log differentiation for. So it's not really a rule. It's not something you can write down a sentence for, because it's a general method, right? It's a list of steps that you go through, right? You log both sides. You bring the powers down, you differentiate implicitly, then you solve for the prime. Right? So it's not really a rule, it's a method. But yeah, I think today's the last day to drop, so I'll talk to you guys after class if you need to talk to me about anything, about tips. As far as, because as I said in the email, I don't think anyone in this class is actually just lazy and slacking off. I know you guys are actually working, but I felt that there were reasons that it's not working out the way you wanted to at the moment. And I threw out some ideas, but of course I have to talk to each of you personally to find out what's really going on. But sometimes what happens is, and this is not just for math class, like in general, right? If you're trying to go after a goal and you're working really hard and you're not getting that goal, you should probably change what you're doing. You know what I'm saying? So if you're reading flashcards all the time and you still can't write down the rule on a test, maybe flashcards isn't what you should be doing, right? Try something else, right? And one thing you want to know is you really want to know yourself and how you learn, kind of, because when your brain is used to working a certain way, it actually does that with everything, but it might not seem like it. So it's, for example, we know you remember some things, right? right? You remember your name, your birthday, your mother's name, your mother's birthday, you remember your anniversary for something else, right? There are a lot of facts in your head, right? So you kind of think, how did you memorize those facts, right? Did you have flashcards memorizing your mom's birthday, right? Like, try to think how your brain actually worked. When you actually got some large amount of data memorized, what did you actually do to accomplish that, right? And really understand it. And you kind of have to roll with what works for you. Just because someone else says, oh, I use flashcards and I remember, it doesn't mean that you should use flashcards, right? And if you tried the flashcards thing and it didn't work, it means you should be doing something else, right? You sort of have to adapt. You roll with the punches. Right? Not everything will go as planned all the time. You just change the plan, right? Remember the overall goal, to know these rules like I know my own name. If this method isn't working, I have to do another method. There has to be something else, right? As well as make sure you're actually doing the flashcard thing correctly, right? So another thing is, just if sometimes when you try to memorize a rule, but you don't know what the pieces are, like you didn't know that this part in the rule is supposed to be a constant instead of a variable, your brain is going to get mixed up anyway. You have to not only be memorizing it, but you kind of have to know what it is you're memorizing, like what the components mean, what they are, right? You want to give your brain some sort of context, right? And that's a lot of the times why you would remember something without going to that extreme, right? Like you remember your mom's birthday or whatever, not because that list of numbers or that particular date is important, but it's your mom, right? You see her every day. Hopefully you like her, or, hopefully she's someone you depend on and you talk to, and there's a whole context, there's a whole story of why it's important to memorize this particular date as opposed to some other particular date, right? So for this particular date, you don't have to use flashcards because there's a context surrounding it, right? You sort of want to build up the same scenario with your math class. Build as much context around the thing as possible, right? And that tells your brain it's important to remember this, it's important to know it from several angles, and you'll actually start to remember more, right?
So each derivative sheet is worth 4 points?
Yep.
So that's 8 points a day?
Yep.
But it's still only 5%
But it's only
of your
5%.
total, right?
Yeah, it'll still only count for 5%.
Wait, so does that help us or not?
Yeah.
It's like additional ones, it's usually like the distribution sheet.
As I said, I'm creating context, right? So a lot of you guys now are like freaked out about the class, right? So before it was like, oh yeah, guys, know the rules. Oh yeah, know the rules. It's going to cost you 8 points a day, 5% of your grade, and you're kind of in a bad position right now. Now it's important for you to know the rules. You get what I'm saying? I'm creating a context.
But there's only something to lose, nothing to gain.
Yeah. You gain 8 points. I mean, it's relatively easy to gain 8
Wait,
points.
8 points in addition to the homework?
No, it's all in the homework. It's a part of your homework grade. It's a part of your homework grade now. This is just new homework that you have to do.
Oh, alright.
When's our final? July 27th, right?
Yeah, it's the last.
Like
And our last test is the last class.
What's the last class? 3 weeks.
Yeah, well, about 3 weeks.
We have one more exam before the final, right?
We have 2 more exams.
2 more.
It's doable. Don't give up.
Where's the
Unless,
test on the 26th?
you kind of have to. I don't know.
26 is the fourth.
No, it'll be the week before the 26th. The Thursday before the 26th. The 26th is actually, the 26th is actually in finals week. So it'll be the Thursday before that, and then the following, whenever it's the 27th.
So we're gonna have a test next week and the week after that. Got it.
Yeah, pretty much.
Do you make our final?
And then
Yeah.
also like three
That's
Will you make the final?
Yep.
Oh, you're making the final?
Nope. By the time you get there, it's gonna be easier. I'm not lying.
See you guys in the fall.
Oh, God.
We'll be in this class again. We're talking about the same things.
So, like I said, it is still possible to come back and get a good grade.
What's a good grade?
Like I see.
An A?
If we put in our effort, that's what he said. So we have to try from this point
Yeah,
on.
so
You could still get an
as
A.
long as it's, yes. So it's all a matter, and I sort of mentioned this email, if it's possible, right? Like I don't know what's going on in your personal lives really, right? Like if you like have to work 60 hours a week, maybe it's just not the right time, right? It is going to take time and effort to do this, but it is possible to come back, right? Just regroup, come up with a different plan, and
Charge for it.
move on.
Okay.
Okay, so derivatives and shapes of graphs.
Do that with your rule. Sheets of rules and put them
We kind of did this already. I summarized it in that table. So I'm thinking of let's just go over that table and restart talking about things. Yeah, where I talked about F and F prime and F double prime and what it does and all that stuff.
Yeah,
Right.
I've never run that. It's my friends did.
Good.
It's hard.
It tells us. We know.
This is gonna be on the quiz, okay?
So the quiz.
Sure. maybe.
So wait, the quiz, what's the quiz on?
Everything since the test.
Is that related? Bruce?
So it'll cover related rates, it'll cover this, it'll cover maximums and minimums. It will cover,
No, try to
Those are both indicate.
not the exponential over here.
yes.
Yeah, that's after.
Yeah, so 3.6 onwards. And I might just throw in some rules on it just for fun. This is what the power rule is.
And we always have to remember to write d dx.
Yes. Again, for context. So you don't end up in a situation where I ask you for the derivative of 1 over x and you write ln x, which actually happens pretty often. And so it's important for you to know what the context is in which you're working. Because what's happened is there are a lot of times where I see students and they're like, they say, I thought I did better than this. I can't believe I did this, you know, like, yeah, you kind of messed up on this problem. That they're like, no way, I knew that. I knew how to do that. And I show them the test. Here's what you did. And I'm like, I can't believe I did this. What was I thinking? It's little things like that that cause that to happen, right? When you sort of memorize something piecemeal, right? Whenever you're under pressure, you remember it in piecemeal. And then it messes things up. It only takes a little tweak right here and then everything is wrong. Yeah, so the original function f of x, what does it tell us?
It tells us the coordinate on a graph.
Right, it tells us points on the graph. Right, it gives us y values for some x value. Right, so it gives you all x, y on the graph. Right, so you should know whenever you're looking for a point on the graph, a location of something, f is the function you should be looking at. Now we know points have the form x comma f of x. Right, so you put the x value here, whatever that value is, put f of x here, meaning you plug that number in. That's how we find them. Plug in x value into f to find y value. So now, that's what a function does. That is what it gives you. It gives you the relationship between two guys that you pair them together. An input and an output, points on a graph that you can draw on a chart. And here's how you would find it, right? F prime, the first derivative, also gives you specific things, right? So what does that tell you about? Tell me the things it tells us about. It tells you about increasing. It tells you about decreasing. It tells you about the locations of maximums and minimums, which is what we did yesterday. That's what the first derivative tells you about. So if someone in a problem, they ask you, find the intervals of increase, find intervals of decrease, find where the maximums are, find where the minimums are. Once that is your problem, f prime is where you should be looking. You should not be looking here. You should be looking here. This is the guy that tells you about these things, right? How we know? Well, f prime is positive, means increasing. F prime negative means decreasing. And basically, how would you find them? First derivative test is how you figure it out, which we covered last time. Right? So basically, you find critical points. Put them on a number line, test the values between them. Critical points is where f prime equals 0 or undefined. So any x value where the derivative is 0 or it's undefined, that is called a critical point. You'll plot those points on a number line and you'll plug numbers into them. Plot these on a number line, test the intervals. You don't necessarily care about the value, you care about the signs. You just care about whether you get a positive or a negative number. So if you have this guy, here's your critical point C. You plug in a random number over here, and you plug in a random number on this side. And you plug it into the first derivative, right? And based on what you get, so if you plug this into the first derivative, you get a positive answer. You know that that's a plus, that means increasing. You're going up. If you're negative, it means you're decreasing. If you're increasing then decreasing and you're continuous, it means you had a maximum, right? Or you can have vice versa happen, right? So if you care about increasing, decreasing, maximums, or minimums, the derivative is who you're looking at. This is how you figure out whether it's increasing or decreasing, and this is how you can find maximums or minimums or intervals of increase or decreasing. Do the first derivative test. Cover that down again. You know what you guys are doing.
The shape of the graph for f of x would be linear, right?
The what?
The shape of the graph.
It's not necessarily linear. It could be general. When we're doing curve sketching, we're going to do a lot more general things. Do we have this? There's a third row, but I'll leave the space. definition, now I'm talking about the second derivative. We talk about what that tells us. How we would know that that's what it's telling us. And how we find it. So what does the second derivative tell us about?
Concavity and inflection.
Concavity and inflections. So if someone asks you to find intervals of concavity or find where the inflection points are, the second derivative is who you're going to look at. You will not look at the original function, you will not look at the first derivative. You will look at the second derivative if this is your goal. Right? How you would know? The second derivative is positive, means concave up. Up like a cup. That means the shape of your graph looks like this. Right? Looks like a smiley face. Right? Your slope is increasing at an increasing rate. The second derivative, negative, means concave down. Down like a frown. And remember, it does not mean increasing or decreasing, that's the first derivative. It just talks about the shape. You can be increasing concave down, but you can also be decreasing concave down, right? So it has nothing to do with increasing or decreasing. It's talk about how you're shaped. Like you can shape like a frowny face while moving up. You can shape like a frowny face while going down, right? It's not about increasing or decreasing. It's talk about how you're curved while you're doing something, right? And I'll talk about a bit more about what that means later. But it's basically talking about your rate of change is increasing, but it's increasing at a slower rate. Or it could be decreasing, but decreasing at a faster rate. That's a concave down behavior. How we find them? Well, there's something called the concavity test. How you want to think of this? It's pretty much the first derivative test, but for the second derivative. So you're going to find the critical points, and you're going to plot them on a number line. So find where f double prime is 0 or undefined. That's going to be your first step. Plot these on a number line. Then you're going to test the intervals. And you test them in the second derivative. And again, we're looking at the signs. So you might have, here's your number line, here's a point. At this point, your second derivative is 0 or undefined. And you plug in a random number in this interval, like an A, and you test it. So let's say you get a positive here. What that positive means in this context, we're testing in the second derivative, that's the function we're plugging in this number into. That positive means concave up like a cup. That means the shape of your graph is this. There's a different interpretation of the sign here. Right? If you have a negative, this means concave down. And by the way, this would mean, right, here, C is an inflection point. Remember, an inflection point is a point where you switch concavity. If f is continuous at C.
So if a question asks us to find the inflection point, we
Right, you do this test, you do the concavity test, and then you identify all the points where you switch from a concave up to a concave down, or a concave down to a concave up. And as long as your function is continuous there, that's going to be an inflection.
How would they word it in a question if they were to ask?
Oh, it's in our examples. They'll work out. It's pretty much going to always be worded the same way. There'll be no llamas or hot dogs or anything. It's just going to be straight up. Find these things and plot the graph. Right. So they'll specifically list what they want. So yeah, it's going to look like this. You're very much, so here's a function, find the intervals of this, find the critical points, find the intercepts, sketch the graph. Yeah. So these are going to be straightforward. Yeah. So just remember, inflection is where we switch concavity. Point where concavity changes. So this table is like super important to know. And in a test, I would make the problems look like the last 3 examples that we probably won't get to today, but we'll probably continue on Monday. But it will look like the last few examples, right? So I'm going to give you the function, and I'll give you the first derivative and the second derivative, so you don't have to find those. Because by the time you get to this point, I would have already asked you about finding derivatives, so I know you can find derivatives already. I don't need to test you on finding derivatives. At this point, I just want you to be able to use them to do something. So you'll be given the function, you're given the first derivative, you're given the second derivative, and you're going to have to go through all these features. Right? So that's basically what 4.3 was about. I just summarized it in the table. We've seen this before. So we're going to move on to curve sketching. Did we all get this?
Yeah. So with all this information, we should be able to answer the homework?
Yeah.
For the most part?
Yeah. So we have a handout for curve sketching. It's already posted on the website. It's kind of covering 4.4 and 4.5 and 1. So here we're going to learn to graph curves in much greater detail. And here are the steps. Pretty much the 6 steps you always go through. Not all the time you'd be asked to do all of them, but you'd have to do them anyway. So you should know this and do that. So it's just putting a lot of ideas that we've already seen together to the goal of being able to draw a picture and figure out how a function is behaving. Right? So we did all the legwork already, so now we're just going to go through a method of how to come up with a picture. Right? So step 1, given a function, you're always going to want to note the domain of that function. Find out where it works or where it doesn't work. So we know things like rational functions, right? When you have a fraction, the denominator can be 0. If you have radicals and it's an even radical, what's underneath has to be greater than or equal to 0, etc. Right? So you just figure out where your domain is, because that's going to come in handy. If your function doesn't exist at a point, your derivative is not going to exist at a point, so that's automatically a critical point. So that's another reason why you should know it. 2, find your x and y intercepts, right? And that's nothing new. We know how to find x and y intercepts. So to find x-intercepts, you set y equals 0, solve for x. And to find the y-intercept, you set x equals 0, solve for y. 3 is probably a little different, but this is why I told you guys about infinite limits in the beginning of the class when we're doing limits, because we're going to use them here. So finding asymptotes, it's how we're going to use limits, right? There are 2 kinds of limits that we care about, the horizontal asymptotes, right, and the vertical asymptotes, right? There are other asymptotes, but we don't really care about them. The horizontal and the vertical ones are the ones we care about. So, for example, horizontal asymptote is just a line that your function tends towards as it goes off to infinity or negative infinity. So you could have some horizontal line, which we write as a broken line, and your function is doing whatever locally, but eventually as it goes off to infinity, it starts approaching that line, right? and it's a horizontal line that it does this with, it's called a horizontal asymptote. Horizontal asymptotes come from limits at infinity, right? So basically, to find a horizontal asymptote, you're going to take the limit as x goes to infinity of your function, and you're going to take the limit as x goes to negative infinity of your function, and you're going to find the answer. As long as your answer is a constant, that is a horizontal asymptote. I have this all written down here, so you don't have to write it. I'm just drawing a picture so you don't have to. So that's all written here, right? So you find these two limits. You have to find both because it's possible for a function to have two different ones. So it's possible, for example, to have a function that looks like this. Right? So as you're going off to positive infinity, it's going towards this line. But as you go to negative infinity, it's going towards another line. Right? So it's important for you to find both limits. Right? It's possible for the limits to actually be the same, but you have to check for both. Right? So that's how you find horizontal asymptotes. You take the limits at infinity. Right? Vertical asymptotes are the ones that happens kind of like around logarithms, or the graph 1 over x has vertical asymptotes. So example of a vertical asymptote, something like a log has a vertical asymptote. It's like that. Or 1 over x will have a vertical asymptote. Right? There's a vertical line that you cannot touch. You'll have other graphs. A little graph, and you can have several vertical asymptotes as well. So it's possible to have a graph that looks something like this, for example. You can have a graph that branches off into 3 parts like that, right? Notice that y equals 0 is a horizontal asymptote. This graph is tending towards those, but there are vertical asymptotes here and here. And how do you know when you hit a vertical asymptotes? Your graph will literally shoot down to negative infinity, or it will shoot up to positive infinity. So all you need to do is find out where this happens, right? So you want to know, you're basically going to want to find A so that if I take the limit as x approaches A of the function, I get plus or minus infinity. For rational functions, it's always going to be where the denominator is 0. This sort of behavior will always happen for a rational function, right? And those are the main ones that you're going to see here where we need asymptotes. Yeah, so that's asymptotes. It's basically limits at infinity and infinite limits. And we have a bunch of examples to go through, so by the time we're done with this, you'll be very familiar with this. For us to find where your function is increasing and decreasing, right? Find the local maximums and minimums if they exist, right? So it's important that for this function I know that, hey, I'm increasing here, and I'm increasing here, I'm decreasing here, and I'm decreasing here. I need to know when should my curve be going down versus when it should be going up. And if I hit a hill or a valley, and I need to know that coordinate, right? So, and of course the first derivative test is what helps you with that. Find intervals of concavity and locations of inflection points if they exist, right? So the graph I had here has an inflection point here, right? This graph has no inflection points, but that's again from the table that we've been doing. And with all that, you're going to put it together, you're going to sketch the graph, which we're going to do some examples on how to do that. Yeah, I also have a paragraph here about some common mistakes that I've seen. I also put a lot of footnotes here so you can read extra information about these things. So yeah, watch your algebra, be consistent. So things like that I see all the time, which I don't really understand. So someone will find intercepts, right? And they'll say, oh, there's only one X-intercept. Yet they'll draw a graph where there are 2 X-intercepts. And say, you just told me there was 1 X-intercept. Why would you draw a picture where there are 2? So things like that you should look out for. It happens more often than you do. Another mistake is not knowing that table that I just gave you, right? Not knowing when you should use F versus F prime versus F double prime. So those are some common mistakes I listed here. So you should really read these through and kind of know them.
What's the O?
What? Oh, a hole is like when, a hole happens to be when the denominator is 0, but the numerator is also 0 at the same time. Right, so if you're looking at your function like y equals x squared minus 4 over x plus 2, right? Notice that when x is minus 2, you divide by 0, but x is minus 2 also makes the top 0. If both the top and bottom are zeros, you don't get asymptotes, you get a hole, right? So it's like your graph is doing whatever, and there's just a gap, right? So instead of doing an asymptote thing, you'll get a hole. Because what it means is that you can actually simplify this function to get rid of the bad point, right? But because it was there in the original, you actually still can't touch that number. You still can't touch minus 2 because the original function doesn't work there, right? But technically, this will behave just like a straight line at all other points, right? So you get a hole instead of an asymptote. Something like this will happen if the denominator is 0, but the numerator is not 0 at the same time. Like you can't factor and cancel something. So yeah, a hole is just like a gap in your graph. A single point that's missing is called a hole. Okay, so let's actually do this. So I have two sets of examples here. Some are easier, right, just to get us in the groove of going through these steps. And then the last three examples, those are the kinds that you'll see on the test. It will be very similar. There'll be no curveballs here. Because the process is kind of long anyway. You don't want to throw curveballs, then you have to take like 3 pages to do anything. Okay. So let's do some examples. We start out with an example that we should all be familiar with at this point. The graph of 1 over x squared. So we're going to pretend that we don't know how to graph this at the moment, and we're going to figure out how to graph 1 over x squared. And the problem is going to be, so here I said, find all the important features listed above and sketch the graph. Right? And the problem will be phrased pretty much almost word for word like you see it here. Right? So it says, consider the function f and the formulas f prime and f double prime. Find all intercepts, asymptotes, extrema, intervals of increase, decreasing, intervals of concavity, blah, blah, blah. You'll have to find all of them. Right? So let's actually just run through these steps right now for this function. So step 1 is what's the domain?
Negative infinity to 0, union 0 to positive.
All right. It can't be 0, but everything else is fine. Okay, so that's our domain. 2.
The 2 you would set y equals to the
Right, you want the intercepts. Right? So first we're going to find the x-intercept. How do we find the x-intercept? You set y equals 0 and you try to solve for x, right? This means that 0 is equal to 1 over x squared. In other words, here you have no solution. Right? Remember, a fraction can only be 0 if the numerator is 0. The numerator here is 1. 1 can never be 0. Again, you can see this if I multiply both sides by x squared, I would get 0 equals 1, which makes no sense, right? So this has no solution. So there are no x-intercepts. Right? Going back to a rookie mistake, if you conclude that there are no x-intercepts, and at the end of the day that picture you drew has an x-intercept, something is wrong. Go back and check your work. Either you're wrong here or your picture is wrong, right? But don't just pretend nothing happened. So there are no x-intercepts.
And the y-intercept is literally...
Now we look for the y-intercept. How do we look for y-intercept?
So plug 0 to x.
You plus x equals 0. But guess what? We cannot do that. Right? No y-intercepts. x cannot be 0. Okay, so that's nice. 3. Now we're going to look for asymptotes. Let's start with the horizontal. How do we find the horizontal asymptotes? You take the limit as x goes to infinity and limit as x goes to minus infinity of your function. So here, start with the limit as x goes to infinity of this function. What's the answer?
0.
0, right? The denominator is growing without bound, so that goes to 0. So I take the limit as x goes to minus infinity of this function. I again get 0. Once I get a constant, y equals that constant is the horizontal asymptote.
Wait, how did you do that?
Oh, the denominator is going to infinity, the numerator is staying where it is, right? So I'm taking a fraction where the denominator, I'm dividing by bigger and bigger numbers.
Oh, yeah.
You'll get smaller and smaller and
Oh,
smaller.
wow, that's heavy.
Right. The bottom is head, it's bottom head, yes. So that's my horizontal asymptotes. Let's talk about vertical asymptotes. Right? So again, for rational functions, vertical asymptotes will occur when the denominator is 0. This x equals 0 is a vertical asymptote. So we have both a horizontal and a vertical asymptote. What's the fourth step?
Find the intervals.
Right, so here I want to know where I'm increasing, decreasing, if I have maximums or minimums. How do I figure that out? First derivative. The first derivative is what gives me that information. So my y is equal to 1 over x squared, which I'm going to think of as x to the minus 2. This means my y prime will be minus 2 x to the minus 3, or minus 2 over x cubed. Critical points. This means y prime equals 0 or undefined, right? This is never 0 because the numerator is 2. 2 is never 0. So, but it is undefined when x equals 0. This means x equals 0 is a critical point. So what I'm going to do at this point, I'm going to draw a number line, I'm going to plot 0, and I'm going to plug in any random number to the right and left of 0. So plug in 1 and minus 1, and I'm going to test that with y prime. So I go to y prime and I plug in positive 1. The result is negative 2, right? So that's a negative, which means decreasing. So I know I'm decreasing here. If I plug in a negative 1, negative 1 cubed is negative 1, negative divided by negative is positive. That would give me a positive number. So I know on this side I'm increasing. Now, be careful not to identify 0 as a maximum. It's not a maximum. Why is it not a maximum? Because of the domain. Part 1 says 0 is not a part of our graph, so there's not a maximum. So even though it looks like I'm increasing here and decreasing there, I don't even exist here, so I'm not a maximum point. But what I do know, I know is where I'm increasing. What's the interval where I'm increasing?
Well,
From negative infinity all the way up to 0, right? So on this whole interval, from here all the way back, I'm increasing, I am decreasing from 0 to infinity. There are no maximums and no minimums, right? Because if there were, I would be able to identify them here. 0 was a candidate for a maximum, but I'm not defined there, so I'm nothing. And so that's my intervals of increase, decreasing, my maximums and minimums. Brings me to the fifth step.
Wait, question.
Yes?
Why is it that you drew that little graph in the bottom for sub 4?
This graph here,
Yeah, so I know that you have to find the first derivative,
Yeah.
right? And then,
I tested on a number line. I want to figure out when is the derivative positive or negative,
oh,
right? Because that's how I know increasing is when f prime is greater than 0. decreasing where f prime is less than 0. I know the points where it is 0 or undefined, so to figure out where it's positive or negative, it has to be between them. It has to be between those points. The fifth point is concavities and inflections. What am I going to use to figure out concavities and inflections?
Second derivative.
Second derivative. So I'm going to go to y prime. I know that y prime was minus 2x to the minus 3, and I'm going to find y double prime. This is 6x to the minus 4. Right? Or 6 over x to the 4th. Then I'm going to find critical points, which there's only one, x equals 0, right? So again, now I'm going to do a number line. But now there's only one point to test, which is 0, and I'm now testing this in the second derivative. So I'm going to plug in a random number over here, like a 1, random number over here, like a minus 1. Plug in an easy number that's pretty small, right? I'm not going to plug in 15 or 17, right? Plug in 1, right? The smallest, most comfortable number that you can, right? So I'm going to take 1, I'm going to plug it in here, and what's going to happen? I would get a positive number, right? Now, positive in this context means concave up like a cup, and shaped like a smiley face. If I plug in a negative 1 in here, I still get a positive because my x is being raised to the 4th power. So it's concave up again. Notice that I did not switch concavity, so there are no inflections, obviously. And even if I did switch here, 0 is not in the domain, so 0 is nothing. Right? So all I get from this thing is just the intervals of concavity. So now I know I am concave up on negative infinity to 0 and 0 to infinity. I am concave down nowhere. There are no inflection points. Now that brings us to step 6, which is the finale. Actually draw the picture. Now in general, by this point, you'll have gone through like a page and a half or 2 pages. So what I recommend you do is you summarize all that information that you found on the graph itself. And then you're going to follow
So that says you give us a time to these, like just one? Because it's like the last time.
I'm going to give you what?
They're like on a test contribution, like one. It's like a lot of time.
Yeah, curve sketching is going to be one problem.
Oh, yeah.
Yeah, and there are no other parts to it. Like curve sketching is just like, this is all you got to do for this problem. Just get this graph done. Yeah. All right. So a lot of the other problems with part A, B, C, no, curve sketching just be graph this guy. That's it.
I think that's too much pressure.
So then, right. So you're going to go through all that stuff. Usually, I'll ask you to actually find these. Right. When you get here, you're going to want to summarize all these guys. So you're going to want to plot your x and y intercepts, but we had none here, so there's nothing to plot. We're going to plot our vertical asymptotes and horizontal asymptotes. Right? Now, vertical asymptotes, you plot asymptotes with broken lines, but here they're falling right on the line itself. So x equals 0 was one of the verticals.
Did you draw like adjacent to it?
Yeah, you just draw it adjacent to it. If it's on the axis itself, just draw adjacent to it. Broken lines. So you draw in your asymptotes. Now, if you're a maximum and minimum points, you would plot those points. Here we didn't have any. In the next example we have. Yeah, in the next example we have. And what you do is, I like to put at the bottom just how am I increasing and decreasing. So for example, I know I'm increasing from negative infinity to 0. So, right, so from 0 all the way back, I know I'm increasing. Sorry, right like that, I didn't see it. From 0 all the way forward, I know I'm decreasing. So I write DEC. Then I'm going to look at my concavity. I'm concave up pretty much everywhere. So from 0 all the way here, I'm concave up, CU. And from here all the way back, I'm concave up.
You chose like any point on that y-axis.
Any point on the y-axis? What do you
Like,
mean? No, I'm specifically plotting this interval here.
no, I know. Like, okay, see the x-axis, right? So you.
I'll plot it at the bottom, like all the way at the bottom.
Okay.
Right? You want a lot of space to draw your picture. This is just so that you can glance the information right away. Right? So, now how do we begin?
Don't we have all the information we need?
We have all the information. How do we put it together?
Start at the end.
So I know over here I'm increasing, right? Because that's what this says I should be. I should be increasing and I should be concave up while increasing. I know while I'm going off to infinity, I should be going towards this line. While I'm going to 0, I should be going towards this line. The question is, do I start down here or up here? Why? Because you guys memorized the graph?
It's possible.
Let's say I started down here, let's say by mistake, right? You're in a test, you freaked out, and you said, okay, the graph starts here. What would happen? If I'm increasing concave up, what's going to happen?
You could go up.
You will cross
You're
the
gonna
x-axis.
hit
Boom!
the axis.
I'll hit the x-axis. Should I hit the x-axis? No, there are no x-intercepts. I cannot start down here. I have to start up here. So I know I'm going towards this line from above. I will never touch the x-axis, so I know I never cross it. And then I'm increasing concave up. So that's that side of the graph. Similarly here, I know I'm decreasing concave up, right? So I know I should be decreasing, right? Now you might say, how far should I decrease? Can I do that? No, you can't. You cannot cross the x-axis. You've already solved for this and you know that there are no x-intercepts. I have to stay above the whole time. So I know I should be decreasing, but I'm going to start leveling off before I cross the x-axis, and I have to level off towards the horizontal asymptote. Because as x went to infinity, the graph went to 0. And that's my graph for 1 over x squared. And we will stop there. So actually part B, we actually sketched that in class before. We sketched that with a W. Try to go through the steps and re-sketch that, but now really paying attention to what your concavity looks like while you're doing something. You'll have to find, it'll have maximums and minimums, it'll also have inflection points. Identify them, try part B. We will have a quiz and all the homework. So we did not complete curve sketching, so the homework for this is not due.
Is it going to be on the quiz?
I'm not going to put it on the quiz. On the quiz, I'm going to put everything between exponential growth and decay all the way up to maybe finding a maximum and a minimum.
So like, is the table?
Yeah, I might put in a table and have you fill in the blanks.